Hello and welcome to the second installment of UTDTG gamedev. In the previous part, I shared some ambitious ideas for my dinosaur tycoon game. Now it's time to get down to business and actually start implementing these ideas. After all, great game ideas are a dime a dozen. It's the code that really brings it to life. So join me as I dive into the nitty-gritty of game development and explore the process of building my hexagon map for my tycoon game in Bevy. In this episode, I'll be showcasing the various techniques I explored while generating the hexagon map for my game. From naively spawning a static mesh for each copy of the cell in the world, to exploring a more dynamic cell system that would update the mesh as its neighbors were changed. I tried out many different techniques to find the perfect balance between aesthetics and performance. Ultimately, I settled on a waveform collapse implementation, which will be discussed later on in this video. So join me as I take you behind the scenes on my journey of mesh generation. When starting out in a new game dev project, it can be tempting to jump straight into developing some great visuals for your game. But I've learned from many failed game development projects that success actually lies in doing functionality first. So the first order of business was to find some hexagon assets to use as placeholders in my game. After all, seeing something tangible and interactive does wonders for one's motivation when developing a game. In most cases, you could probably get away with just colored squares and text for your placeholders. But hexagons are sort of a different beast entirely, since they are not as intuitive to work with as squares and rectangles. So finding functional assets that meet the criteria of a hexagon are a necessity more than an option at this point, since if you use shapes that are not truly hexagons, they may not tile properly when you do move to true hexagons. As I set out to find properly constructed hexagon assets for my game, I knew I needed a reliable source. Kenny.nl has been a treasure trove of resources in the past, so I had high hopes for this time as well. And boy was I in luck. Kenny.nl's hexagon kit had everything I needed. The collection boasted hexagon cells, buildings, and different terrains like trees and rocks, basically everything I required to start prototyping a game on a hexagon grid. But the real game changer was the river tiles. It contained all 14 possible combinations. The implications of this will become clear as we explore the different map generation techniques later on. Just to give you an idea, the type of river that you would need to place on a hexagon depends on what neighboring rivers it connects to. This can be incredibly difficult to visualize, but having 14 possible starting positions in order to know what rotation and orientation the rivers need to be in to connect properly really sped up things and pointed out potential issues with some of the approaches. So with the hexagon kit from Kenny.nl, I was fully equipped and ready to start developing my game. So let's dive into the first technique that I used for map generation: static instant copies of the meshes. The instant copy approach is the most intuitive way to generate a map on cells. It's like making a photocopy of a piece of paper, but with 3D models. And with Bevy's entity component system, we can easily create entities for each cell and customize them with different components, like adding water components to river cells. There is a catch, however. Finding a specific cell based on its location is not straightforward with an entity component system. Unlike the array approach, which uses simple math to locate where in the array the cell should be placed, we have to iterate through each entity and check to see if its cell ID is the one we are looking for. To solve this issue, I had to create a resource that would contain a mapping of each cell ID to its corresponding entity, making it possible to look up a specific ID and get its corresponding entity. We can then use this entity in conjunction with Bevy's ECS to find out what components are attached to that cell. As I developed more of the instant copy approach, it became clear that this method had a significant limitation. While it seems like an obvious solution, the fact that you need to know all neighbors at the point of spawning an entity creates a significant roadblock. For example, with those 14 different river types and their combinations of connections to their neighbors, this approach quickly becomes unmanageable. The requirement to set the correct mesh and rotation for each river meant that you couldn't edit the map once it had been created. Otherwise, you risked mismatches between the connections of the rivers and their neighbors. This was the issue that killed the static instance approach, but wasn't the overall issue that killed the instance approach. I'll cover the true killer after the next section, the dynamic instanced approach. With the limitation of the statically instanced approach, I had to think outside the box to come up with a more flexible solution. So the dynamic instanced approach was born. This approach allowed for cells to update in real time based on their neighbors changing. resulting in a constantly evolving and interconnected map. It was a pretty breakthrough moment when I saw all of the rivers connecting properly on my procedurally generated map. This allowed for the creation of seamless river systems that did not require any input from me in order to change the river if I had decided to make it branch in a different direction. This opened up a lot more potential for how the map could generate, since I was no longer required to generate all of the cells, and instead could have the map dynamically resize, since the cells at the edge of the map would then look at their new neighbors and update accordingly. As I continued to test and generate larger maps to ensure that all the cell behavior was working correctly, I began to notice significant drops in performance from Bevy. Trying to fly over the map would reveal a slowdown, and it was slowing down at an alarming rate proportional to the size of the world. It wasn't until I started digging a little bit deeper that I discovered the culprit. Bevy's rendering system does no batching, so it struggles when rendering hundreds of thousands of entities every frame. At first, I was puzzled because I was only spawning tens of thousands of cells. However, as I looked closer, I also noticed that Bevy seems to load GLTFs in a funny way. It splits the mesh up based on the material, which would be all fine and good if Bevy could handle lots of entities with meshes attached. But since each mesh is then spawned with its corresponding material on its own entity as a child of the parent, this makes the rendered entity count significantly larger than the actual number of objects that you think you would be spawning. As a result, Bevy needs to spawn many more entities each frame and copy them to the render world, a process that was also contributing to the slowdown. This limitation may not necessarily be avoidable in a lot of games, but since I wanted sort of a low poly art style with limited colors, this made it possible for me to make each mesh only have a single material that had different parts of the material's texture, and I would simply set the UVs to the correct position in order to create the correct color. But even with this optimization that meant each cell only took up a single entity, Bevy was still unusably slow on larger map sizes. So I had to come up with a way of rendering a few large meshes rather than many small ones. And with this revelation, I realized that the instanced approach for cells was dead. However, I still wanted to maintain that each cell was its own entity, since this allowed for a lot of customization and expansion using the ECS system, since I could add components to cells in order to give them specific functionality or flags for interactions. So instead, I needed to come up with a way of rendering meshes that was not specific to what cell that mesh was attached to. So how do I generate a few big meshes instead of many small ones? Well, anyone who's ever used a voxel game knows the answer to this. It's chunking. It involves combining smaller meshes into larger ones while preserving as much information as it can about the original small meshes. The first step in my chunk generation journey was to come up with a method that would combine multiple cell IDs into a single larger chunk ID. This allows me to quickly work out which chunk each cell belongs to. This can be used during the spawning process to set their parent correctly, or at the generation level in order to work out which chunk this cell belongs to. I then came up with a method that allowed me to use a chunk ID to work out all the possible cells that would be inside that chunk. Using that, I could then look up the entity for each of those cells, work out what mesh I need to bake into that chunks mesh, and create one large chunk mesh that was for all of the children cells. Converting from a cell ID to a chunk ID in a square grid is very simple and intuitive. Just divide the cell's ID by the chunk size and round it to the nearest whole number. However, with a hexagon grid, it is much more complicated because there are 3 values that represent the position of the hexagon on the grid, and these 3 values, when combined, must sum to 0. So, in order to work out which chunk a hexagon belongs to, we need to know a few constants. First off is the size of the chunk as a positive integer, representing the number of hexagons in each direction from the center hexagon to expand this chunk to. Next is the area of the chunk, which is determined with the formula 3 times the chunk size squared plus 3 times the chunk size plus 1. We use these two formulas, which basically take a cell's Q and R coordinate and convert them into a chunk's Q and R coordinate. Similar to with a square grid, we now need to round these to the nearest whole number. However, with a hexagon, we can't simply round the Q and R values. It is more complex than that, since we have that third value, S, to contend with. S can easily be calculated, but in order to round the hexagon, we would need to round Q, R, and S all independently. If we just naively round Q and R though, we may get a different value for the S before and after rounding. This is not acceptable since we need to make sure that Q plus R plus S equals 0. So rounding the individual Q and R has a potential to break this, since the S may round up or down depending on the Q's and R's value if it's done before or after calculating S. To avoid this, we must round Q, R and S individually. We then work out which of these had the greatest movement and discard it. We then use the remaining two in order to calculate the third. After figuring out how to determine which chunk a cell belongs to, my focus shifted to generating the mesh itself. While the straightforward approach of copying every vertex with updated positions into the larger mesh was an option, I opted against it for the performance reasons. The downside of that approach is that it would result in lots of duplicate vertexes along the edges of cells where they meet. So I set out to implement a method of deduplicating the vertexes, allowing me to create larger meshes without any redundant vertices. My solution was to insert each vertex into a hash map, where its position and UV were used as the key, and its index in the vertex buffer was its value. If the vertex was already in the map, however, I could use the saved index. However, implementing this approach came with its own challenges. For one, Rust lacks a hash implementation for floats, so I had to come up with my own approach for hashing the position. Initially, I multiplied the value by 100 and then cast it down to an I64 that then could be hashed. This worked well at first, but I noticed it could create seams between the meshes where vertexes would end up being like 0.1 apart, which on a large scale wasn't necessarily noticeable, but on smaller scales when you were close to the meshes, you could quite clearly see the skybox rendered behind. This would also result in issues in lighting, since two vertexes that should have been the same vertex were not shared and therefore had different lighting calculations. To resolve this, my first approach was to multiply the value by 1000, therefore reducing the potential error by an order of magnitude, and round the position rather than just casting it to an I64, which meant that you no longer had the potential for two vertexes very close together to end up snapping a distance apart since they fell either side of a boundary. This method worked, but still didn't introduce ideal meshing, since it was possible for values to be very close but not quite exactly the same. It is possible that simply rounding on the multiplied by 100 would fix this issue, but instead I decided to avoid accumulative floating point errors by swapping to using an IVEC3 that was a multiple of 1000 of the original mesh, and only convert back to a float once all the meshes have been combined. This minimizes the number of floating point operations performed, and therefore minimizes the potential error accumulation over the course of combining meshes. These new meshes were performing well in terms of speed, but I encountered a major limitation with the low poly art style. Since I was only utilizing position and color to determine which vertexes to merge, there was no way of determining what lighting effects would be applied. This resulted in it being very hard to detect changes in elevation, as a result of the lighting being smoothed across all of the hexagons during my testing. To remedy this problem, I made a copy of Bevy's PBR shader and made it calculate normals for each face at runtime. It would calculate the normal as the tangent of the current face. This resulted in your stereotypical low poly lighting, and did not require me to duplicate vertices that would be needed in order to do purely perpendicular lighting. However, since I am not very familiar with shaders, I am currently using a workaround in order to calculate UV coordinates that result in a color from a palette texture that I load. This is very far from efficient since I need to use two floats in order to represent the UV coordinate of each vertex, which totals 8 bytes. The same effect could be achieved by only using a single byte representing the index of the color in some kind of color lookup array. If you have any knowledge of shaders and are willing to help, please feel free to reach out to me in the comments or on Discord. Or if you know of some good examples of single color polygon shaders that I could look at in order to work out how to make this shader more efficient in the future. While working on the chunking code, I did move away from using Kenny's prefabbed hexagons that I brought up at the beginning of this video. I had to change to more simplified meshes so that it was possible for me to hand calculate what the hexagon should do while I was testing my code. Unlike what I was doing with the prefabs, where the difference between two hexagons was great, in order to test the chunking code was actually chunking correctly, I needed to be able to comprehend what the hexagons were doing, and Kenny's models were far too complex for this. So this brings us to the third approach I tried for hexagons. This I call voxelated hexagons. With this technique, I would generate the map as a height map for each hexagon position, and this would construct the ground plane that other meshes would then be placed on top of. Originally, I started with 6 vertexes per hexagon and made each vertex's Y position equal to the average height of the 3 hexagons that would share that vertex. Though this somewhat worked as long as the mesh was relatively flat, it did not look very visually appealing when multiple hexagons had significantly different heights, since the polygons I was drawing were not guaranteed to necessarily share a nice plane with their neighbors. Another approach I could have tried, but didn't end up actually implementing at any point, would have been to put a central vertex and generate 6 triangles instead of 4 in order to represent the hexagon, where the center vertex would be set to the specific hexagon's height. The main reason for not using this approach is it is very similar to the generic triangle mesh generation that you will see in a lot of examples of procedural terrain, since all I'm really doing is generating individual triangles to represent the height map. The only real difference being that mine was sampling the height map on a hexagon grid as opposed to the square grid that most triangle meshes would sample. So instead, in order to try and up the hexagoniness of my maps, I decided to increase the number of vertexes to 12. This would allow me to create a flat hexagon in the middle that's height is set to this hexagon's height. I would then draw 6 trapezoids that connect that center small hexagon to the larger outside hexagon that the 6 vertex approach was creating. While this method had some promise, it had one unremediable side effect. When the hexagons to the left and right had a higher average height than the one directly above, it would cause a mound to appear in the mesh, since the average of those points would be higher than the neighbor. So that's when I had to take the approach of increasing the vertex count one last time to 24. With 24 vertexes, I could use 6 to create the flat hexagon in the middle, 6 for the averaged corner positions, and then 6 sets of 2 to create the straight connections between each hexagon and its neighbor. With the 24 vertex approach, I was able to achieve the exact terrain that I had envisioned when I was drawing it out on paper. However, while I was admiring my new terrain generation, I couldn't shake the feeling that there was a better way of doing it. As I delved deeper into optimizing my chunking approach, I realized that using a fixed number of vertexes to connect hexagons was not the most effective way to achieve the desired result. After some brainstorming, I came up with a method that involved using a set of connection types to break up each cell into 13 segments, 6 corners, 6 straights, and that one center hexagon. By using this approach, I could create a submesh that fits into one of the 3 segment types, additionally making variants of this submesh for each possible type of neighbor that this hexagon could connect to in that position. This allowed me to have more versatile edge types than the fixed position and number of vertexes would allow. This new approach would then also allow me to have sub-hexagon sized rivers, and even more reactive rivers than the 14 variants that were provided by Kenny. For example, I could add different straight segments for if the hexagon that it was connecting to was made of dirt or sand, giving either a muddy bank or a beach effect. Or on hexagons making tight corners, I could remove the centerpiece of dirt in that corner if I knew that the 2 rivers it was connecting also connect to each other, allowing for me to make small modular lakes. This approach removed all limitations on the number of types of submeshes that I could specify. All I needed to do was make sure I knew what possible neighbors I want this submesh to be able to connect to, and as long as I had a set of rules for what that neighboring hexagon would try and connect back with, I had nearly infinite possibilities. This also removes the need to generate multiple meshes of every possible combination, which can grow exponentially as different connection types get added. I only needed to factor in at most 3 connections in a segment, since it can only ever be a corner piece that connects to itself and the 2 neighbors that are adjacent. Every other possible combination that a hexagon could be placed in would be generated as a per segment calculation, resulting in the complexity dramatically dropping off. As I reflected on this method more and more, I realized it resembled the waveform collapse algorithm. Each hexagon would start as a cloud of possible segments that could be placed in each of its possible 13 positions. Then, by looking at the neighbors of each segment, I could systematically remove what possible pieces could fit into that segment. This is identical to how waveform collapse removes the possible meshes that it considers by looking at the neighbors. It was also at this point that I developed an asset loader that would convert OBJ files into wave meshes. I used OBJ files since they are a fairly simple and easy format in order to write a parser for. They also allow for multiple objects to be saved into a single file. This allowed me to have a wave mesh and all of its sub-segments saved into a single file without needing to load lots of files all at the same time. This also allows me to create meshes in Blender and export them with the correct names into my game. With this new asset loader, I can now quickly and effectively create wave meshes that could be seamlessly integrated into various types of wave objects. Moving on to what I call wave objects. This was a trait that you needed to implement onto all objects that could possibly have the waveform collapse applied to them. It has a method that takes in a reference to all of its neighbors, along with some additional metadata needed to create the mesh. It would then return to you the specific mesh. Once I've determined what a cell will look like, I can merge all of its segments into the chunk using the hash map method detailed earlier. And just like that, a whole chunk mesh can be created. And I don't need any mutable reference to any of the cells themselves. Once the mesh is created, I can simply insert it to the chunk entity and Bevy will take care of the rest. I'm particularly excited about the multiple types of wave objects that I've already implemented. This being a flat wave object, a pathing wave object, and a dynamic wave object. And with just a bit of polar noise, I can create some really nice looking maps already. The flat wave object is used for things that do not dynamically respond to their mesh to their neighbors, such as grass, which will always connect to its neighbors exactly the same. The path object is used to create things like rivers that need to look at their neighbor and decide what connection type they are going to use in order to connect to the neighbor correctly. And finally, the dynamic wave object leverages its unique cell ID in order to spawn random decorations on itself. It also looks at its neighbors in order to determine what type of decorations it may want to spawn. This, for example, allows for forests to change density based on their position internal to the greater forest. If I have a forest tile on the edge of a larger forest, I want it to have smaller trees and more shrubs than, say, a forest tile completely surrounded by other forests. This can result in really nice transitions between forests and other biomes. But as always with these sorts of things, I'm faced with a new challenge. While I want the wave object to be read-only, I need a way of it being able to communicate to its neighbor what sort of connection it has with it. Currently, I'm using an array approach that has each wave object declare what connections it can make. The order at which these connections appear in the array is the preference that it would like for these connections, i.e. the first element in the row should always be used if both systems agree that that is the best. However, this method is one-directional, meaning it is possible for connections to not be lined up correctly, which is far from ideal. The current solution I'm using to fix this is to run the algorithm twice, once with cell 1 being the primary cell, and once with cell 2 being the primary cell, then comparing the two results from these cells. If they match, great, use that one. If they don't match, I use the connection type with the highest priority of those two. This is far from ideal because it means at creation time I need to arbitrarily decide which connection is preferred over a different possible connection. I've done some research into the stable marriage problem and the Hungarian algorithm, but both these have requirements that as many elements as possible must be used. So may sacrifice the optimal pick for the first choice in order to get a better optimization on the second and third. Whereas my approach only cares about getting the absolute best optimization on the first pick only. So I'm hoping down in the comments you guys can leave some suggestions of other types of algorithms I could look into in order to determine the best algorithm for picking the ideal connection between 2 or 3 hexagons, depending if it's a straight edge or a corner piece. So my modified waveform collapse is the final approach that I have currently implemented. I may in the future explore other implementations, but my focus at the moment is on prioritizing parallelization of my systems. I've made quite a bit of progress in parallelizing my approach. The only issue is that it is currently coupled to Bevy's frame update logic. This means if a single chunk takes too long to generate, it will slow the entire frame time down. This also means that only a single chunk will be generated per frame, even if it is possible to generate multiple chunks per frame without slowing the frame down. Currently, I generate enough chunks per frame in order to saturate the number of cores that Bevy has available for parallel processing. This means that my current generation of chunks is 1 chunk per frame per core. This is alright for small maps with lots of small chunks, but on larger maps where more complicated chunks are being generated, or larger chunks are generated, this can result in long periods of frame lag where the chunks are being generated. To address this, I have 2 potential ideas that I will implement before the next video. The first is to add some kind of pause resume style to the generation. where X number of threads are given 16 milliseconds per frame in order to generate the chunks. If they don't get a chunk finished in that time, they can pause and then resume that chunk in the next frame. This is great because on more powerful computers, more than one chunk can be generated per frame per core, whereas on slower computers, it may take multiple frames per chunk per core. I'm also leaning towards this approach because it would not require any significant changes to how I own data. I can simply use Bevy's resource system in order to contain the data, since it will not be borrowed for more than the length of a single frame. The second approach, however, is to try and get Bevy's async threads working. Bevy has a handful of async threads that are used to manage tasks in the backgrounds, which would remove all the overhead and time delay that comes from pausing, resuming, and tracking the duration of the current threads. But the big blocker at the moment with this approach is that I need access to wave meshes and wave objects during the mesh generation process, and it would be tricky to implement this within the ECS framework, as I would need resources to be borrowed for longer than a single frame. If you have any suggestions or ideas about other things that I could use for async mesh generation, please feel free to leave them in the comments. I'd love to hear your approach and ideas. Thanks for sticking with me until the end of this devlog. I know it's been a really long one, but I had so much to talk about with all the different approaches that I have taken. If you've found this video helpful or just enjoyed hearing about the different approaches to generating mesh chunks, don't forget to give the video a like and share it with your fellow game developers or anyone who you feel would be interested in my Dinosaur Tycoon game. Your support really means a lot to me. If you have any ideas or feedback, please leave them in the comments below. As we all know, the YouTube algorithm absolutely loves engagement in the comments, and I like hearing from other people's perspectives on what they think I should do in my game development. This is a great way of learning new approaches and concepts in game design. A great example of this is I gave ChatGPT one of the functions that I use to combine meshes together, and it suggested a single line change that doubled the speed at which my code would generate, simply because it knew a method existed that I did not. This is why I believe it is incredibly important to always hear other people's perspectives on how they would implement your approach. If you would like to support the channel, you can find my Patreon linked in the description. Any contribution on my Patreon page will go directly back into improving the quality of my content, such as getting someone to professionally create thumbnails. As a Patreon supporter, you will also gain access to the source code of this project, so you can get a closer look at how I implemented some of these different approaches in my game. Alternatively, you could also reach out to me on Discord if you have any questions relating to this video or any other video that I post on my channel. I love to help anyone with their problems in Bevy, but also love any contribution to my projects. So thank you very much for sticking to the end of the video, and I will see you in the next one.